Welcome to today's webinar, Developing Chemical Kinetic Mechanism in the Computational Chemistry Consortium, brought to you by Convergent Science. Thank you for joining us today for the 12th installment of the 2024 CONVERGE webinar series. My name is Matthias Sulis and I'm part of the business development team at Convergent Science. I will be your host for today's event. I'm glad I can be here with you today and learn the latest news from the Computational Chemistry Consortium and to attend the demo of the newest tool available in CONVERGE Studio for mechanism extraction and reduction. Convergent Science is a rapidly growing computational fluid dynamics software company. Our flagship product, CONVERGE, is an industry-leading CFD solver used around the globe to simulate fluid flows in complex systems. CONVERGE features truly autonomous meshing, which eliminates all user meshing time and helps provide fast, accurate results for our clients. Now it is time to introduce our speakers for today's event, Curran and Pradeep Sapkota. Professor Curran received his PhD in experimental and numerical studies of combustion kinetics from the University of Galway in 1994, and a Doctor of Science from the National University of Ireland in 2011. He is currently director of the Computational Chemistry Center at the University of Galway. Professor Curran is a founder member of the Irish section of the Combustion Institute and a fellow of both the Institute of Chemistry of Ireland and the Royal Society of Chemistry. He was awarded the Boyle-Higgins Gold Medal in Chemistry by the Institute of Chemistry of Ireland in April 2017, and the Yakov Zeldovich Gold Medal by the Combustion Institute in July 2022. Professor Curran became Chief Technical Advisor on Chemical Kinetic Modeling with Convergent Science in 2017. Pradeep is a Senior Research Engineer on the support team at the Convergent Science World Headquarters in Madison. He received his PhD in Aerospace Engineering and Mechanics from the University of Alabama, where he worked on a machine learning technique to model turbulent jet behavior. Without any further delay, I will now pass the ball to Henry and Pradeep. Thank you all.
Thank you very much. Today, I'd like to share with you the current mechanism developments that are occurring in the Computational Chemistry Consortium. And we're developing mechanisms from hydrogen oxidation to soot formation. Okay, so the C3 technical team comprises my group at the University of Galway, the correct modeling group at the Politecnico di Milan, led by Tiziano Faravelli, the Institute for Combustion Technology at Alkanes University, led by Heinz Pitch, the Lawrence Livermore National Laboratory, led by Scott Wagnon, Argonne National Laboratory by Stephen Klippenstein, and the Convergent Science team, led by Kelly Senecal and his team. Okay, so what we're trying to do in the Combustion Chemistry Consortium is develop a mechanism starting with the hydrogen-oxygen mechanism all the way up through the C4 core chemistry, adding then larger hydrocarbon chemistry, and then polyaromatic hydrocarbon and soot chemistry also. And within the mechanisms, we also have various oxygenated species, including methanol, ethanol, dimethyl ether, and also some pollutant chemistry, including aldehydes and NOx chemistry. Haven't added SOx chemistry yet. And each group is working in different components of this mechanism development. Okay, we published a mechanism, C3 Mech version 3.3, online in December 2021 in Applications in Energy and Combustion Science, and this mechanism is freely available online at the fuelmech.org website. Now that mechanism was updated to version 3.4, where we added ammonia chemistry to the chemistry, and then upgraded subsequently to 3.5, where we updated some of the toluene chemistry also. And all of those mechanisms, C3 Mech version 3.3, 3.4, and 3.5, are all available on the fuelmech.org website. Okay, in C3 Mech version 3.3, we validated all of these components, including hydrogen, carbon monoxide, so syngas, and then methane, methanol, formaldehyde, and all of these components, including n-heptane, isooctane, n-decane, n-decane, n-dodecane, toluene, phenol, and all of these components are validated against shock tube and RCM ignition delay data, jet stirred reactor, flow reactor, and flame speciation data, and also laminar burning velocity data. So everywhere there's a tick here, we validated the mechanism against those data over a wide range of temperature, pressure, and equivalence ratio. And mostly what we did was we validated the mechanism for single components, okay? And so the mechanism includes important surrogate fuels for gasoline, diesel, and jet fuel, biofuels like alcohols, dimethyl ether. It has detailed PAH chemistry and it has detailed NOx chemistry. And it can be used to generate surrogate mechanisms of gasoline, diesel, and jet fuel, predict ignition delay time, laminar burning velocities, species profiles of all of the validated species over a wide range of conditions. And also it can predict NOx and PAH emissions. Okay, so since the publication of C3 MEC version 3.3 in December 2021, we've been further developing the mechanism. We now have C3 MEC version 4.0, and I'll be discussing mostly the updates to the mechanism. In the C0 to C4 updates, we've included a lot of blends, so including hydrogen blends, including hydrogen methane, hydrogen propane. We've included ammonia chemistry and updated the ammonia chemistry further from version 3.4. We've published on hydrogen ammonia blends in a publication earlier this year in Combustion and Flame. We've looked at ammonia hydrogen, ammonia methane, ammonia methanol, and ammonia and heptane blends. And we've looked at methane DME blends, ethanol DME blends. We've added some solvent for batteries like dimethyl carbonate, diethyl carbonate to the mechanism. We've added alcohol, including N-butanol. We've looked at vinyl acetylene chemistry. We've added cyclopentadiene and cyclopentane and cyclopentene chemistry to the mechanism so that we can include some cycloalkane and including cyclopentane as a surrogate for cycloalkanes in gasoline and diesel surrogate mechanism development. And we also looked at then cyclopentane and blends with DME, DIB, toluene, and multi-component blends also. We've looked at methanol and heptane blends, and then looked at DIB1 and DIB2. DIB1 is 2,4,4-trimethyl-1-pentene, DIB2 is 2,4,4-trimethyl-2-pentene. And these chemistries have been added to C3 MEC version 4.0. We've also other components added, like 2-methyl-decane. We've looked at hydrogen n-decane and methane n-decane mixtures, and I'll be talking about these. And we've looked at lots of different blends of natural gas and NOx blends with different natural gas mixtures, and the effect on ignition of adding NOx to natural gas blends. So that's for exhaust gas recirculation studies. Okay, so I'll just give you a flavor of the kind of thing we are doing. So all of the technical partners are really interested in developing detailed chemistry and accurate chemistry. So this is just looking at an example of looking at H plus O2 plus argon. This reaction is very important in this temperature regime, where it competes with H plus O2 giving O plus OH, which is the most important chain branching reaction in all of combustion. And so if this reaction occurs, H plus O2 plus argon giving HO2 plus argon, that's a propagation reaction, not branching, and it inhibits reactivity. And you can see here, all of these data points are experimental measurements of the rate constant. And then these lines are model or calculations of the rate constant. And you can see that there's some uncertainty, particularly in this important temperature regime. There's a band of uncertainty here in the rate constant for this reaction. And what we've done is we've refit our rate constant such that we follow the lower low pressure rate constant at 0.1, 0.01, 0.11, and 10 atmospheres. And we follow the higher rate constant at 30, 100, and 300 atmospheres. And in that way, we get better agreement of our model with ignition delay times measured in the literature. So here are some ignition delay times measured at 1, 13, and 32 atmospheres. So our previous mechanism, C3 mech version 3.3 or 3.5, it's exactly the same hydrogen chemistry compared to C3 mech version 4.0. So the 4.0 predictions of the solid lines, the dashed lines, are the previous mechanism predictions. And you can see that certainly at the lower pressure, we improve agreement, but even at the higher pressure, we're also getting better agreement with the ignition delay times for pure hydrogen by doing this. Also, we've looked at how we simulate RCM data, and we've improved that. And in improving our predictions of the RCM ignition delay times, our updated predictions, which are the red lines here, better match the experimental data compared to the blue line predictions, which we had previously. So we're understanding how to simulate these data more. And if we then compare our current model predictions on the right-hand side here for 20, 40, and 50 bar, the model is accurately capturing the ignition delay times for pure hydrogen, whereas our previous predictions showed that we were actually under-predicting the data, which isn't the case. Okay. We've also looked at flame speed predictions. So here are typical hydrogen flame speed measurements at 1 atmosphere and 298 Kelvin. And what we see here, the points are the experimental results and lines are model predictions. This dashed line is actually using our chemistry, but with Lennard-Jones parameters for the H atoms, which are used in most detailed chemical kinetic mechanisms. So here are the Lennard-Jones parameters. We have the collision diameter, and we have the energy loss per collision. And you can see then we've also plotted on this graph a calculation performed by Aaron Jasper working with Jim Miller and also Stephen Klippenstein. They published a couple of papers on this in 2012, 2013, almost a decade ago now. But these parameters have not been adopted by the community in chemical kinetic mechanisms. And you can see that if we use the Jasper Lennard-Jones parameters for H atom, our predictions go from the dashed line predictions here to the solid line predictions. So in the dashed line predictions, we're under predicting flame speed, whereas with the black line, we're over predicting flame speed. And what we see is that if we then adjust the collision diameter, we change it from 1.53 angstroms to 1.84 angstroms, we can actually match the measured flame speeds very well. Okay, and you can see over the range of equivalence ratio from very lean all the way up to 5, we have very good agreement of the model with flame speeds. But if we scroll down here, we zoom in on this lean data in this range, you can see that the previous models under-predicted the flame speed. And now we're actually getting better agreement with the flame speeds. It's a bit faster, but still not as fast as what measured experimentally. Okay, but the agreement that we're getting, or the improvement in agreement, is stemming from an analysis of this rate constant, the hydrogen plus O atom giving H plus OH. And you can see here again, these points are experimental measurements, and the lines are fits to those rate constants. You can see the solid black line was a previous fit that we're using, which wasn't a very good fit to the data. We've now improved the fit to this red line, and we're getting that leads to this better agreement with these flame speeds at lean conditions. And that's important for a lot of studies nowadays. Our focus within the combustion community is on lean hydrogen combustion. And so we're improving the mechanism prediction in that regime. We've also, similar to the H plus O2 plus argon, we've looked at H plus O2 plus nitrogen, giving HO2 plus N2. And again, you can see that within the range of temperature of importance here, in this range, that there's a window here of uncertainty in the rate constant. And so we're adopting the best rate constant we can to get better agreement with ignition delay times and flame speeds. So our current model predictions now are the solid lines, and the previous model prediction of the dashed lines in all of the plots that I'm going to show you. And you can see here for a range of flame speeds of 1 atmosphere and 298 Kelvin here in different dilutions. So we have helium diluent, argon diluent, nitrogen diluent. We've improved the model prediction of the flame speed measurements. Okay, and again here at higher pressures at 10, 15, and 20 bar, we've improved agreement slightly of the model compared to the experimental data. Okay, we've a big focus of C3 Mech version 4.0 is actually looking at lots of mixtures, including binary and multi-component mixtures. So I'm going to be showing lots of examples of these now. So for instance, hydrogen, CO, syngas, ignition delay time, and flame speed predictions. Again, the solid line is the current model predictions, the dashed line is our previous model predictions. And you can see here, we've improved agreement against these syngas ignition delay time measurements of 1, 6, 4, and 16 atmospheres this is for a 50-50 hydrogen CO mixture at 5.5, and this is a 5% hydrogen, 95% CO mixture, again at a lean condition of 5.5. Okay, here the agreement is a little bit worse at low temperature, but overall we're improving agreement of the model compared to the experimental data. And here again, you can see that there's generally improved agreement of the model against these syngas mixture data for ignition delay times. We've also improved, at least on this side, at higher pressure, 5, 10, and 20 atmospheres, we've improved slightly the agreement of the model against these experimental data. At 1 atmosphere here, it appears that the model is slightly over predicting the measured flame speeds, particularly in the peak. Okay, but here again, you can see this is over a range of 1, 2, 3, and 5 atmosphere data. We're looking at the effective equivalence ratio, and for this mixture of syngas at higher temperature, and you can see that the model slightly faster, and it's in better agreement with the experimental measurements generally. Both models are quite good, but I would say the new model is slightly better. Okay, so in general, then the model for a wide range of conditions, including hydrogen, methane, methanol, ethane, ethanol, and ethylene, that in all of these cases, the points are experimental results and the lines of the model predictions, and the model is accurately capturing the measured flame speed over a range of pressures and equivalence ratios for all of these single component mixtures. Here we have acetaldehyde, acetylene, and propane, propene, allene and propyne, and N-butane at 2 different temperatures. And so oftentimes the data are measured at different temperatures, different pressures, and we're plotting them all here. And so this, having such a wide range of validation against all of these targets for C0, C1, C2, C3 species, C4 species, gives us confidence that the model is accurately capturing the laminar burning velocities of all of these conditions. Okay, so now I'm going to change direction a little bit, talk about hydrogen addition to methane ignition. And here, this is a study that we performed, we published at the proceedings and in the last symposium. And we were looking at different mixtures. So here we're looking at ignition delay times for pure methane, are the black points, pure hydrogen are the blue points, and then a 50-50 mixture of hydrogen methane are the red points. And what we see, particularly at phi is equal to 1 and phi is equal to 2, that once we get below about 890 Kelvin, what we see is hydrogen is slower than methane to ignite. Okay, and that particularly you can see it here, the 50-50 mixture has intermediate reactivity, but again, hydrogen is slower than methane to ignite here. So I'll explain why in a second. We also looked at, through the years, in the last number of years, we've looked at natural gas n-alkane blends. And blends of natural gas with high concentrations of methane all the way up to ones with low concentrations of methane, but higher concentrations of higher order hydrocarbons, okay? And so as we progress from NG1 here to NG10, we're progressively getting higher and higher concentrations of higher order hydrocarbons. And here we plotted results of ignition delay time measurements at 20 bar and 30 bar for a number of these different natural gas mixtures, NG2, 3, 6, 7, 8, and 10 on both of these graphs. And what you can see is that the blend with the highest concentration of methane is slowest to ignite, and that with the highest concentration of hydrocarbons is the fastest to ignite, and those with intermediate concentrations are intermediate to those. But again, the points are experimental measurements here of ignition delay times. The lines are model predictions, and you can see that the model is accurately capturing the ignition delay times. These are shown simulations using C3 MEC version 3.3, but version 3 or 4.0, we haven't lost the good agreement that we have. We've retained it. So they're pretty much identical to what I'm showing you here. So if we then look at maybe hydrogen addition to natural gas mixtures, and this is just a theoretical calculation, we don't have experimental measurements, but the model is accurately capturing the reactivity of these. What we see is that the model predicts that at low temperature, the NG mixture here is fastest to ignite, and then as we add more and more hydrogen, the mixture becomes slower to ignite at lower temperatures. And then when we reach about 950 Kelvin, all mixtures have the same reactivity. And at temperatures above that, the blend with the highest concentration of hydrogen is fastest to ignite, with the highest concentration of natural gas are slowest to ignite at higher temperatures. So there's a duality in reactivity here. And that's stemming from the fact that if we look at sensitivity analysis, we see that the most important reaction inhibiting reactivity is hydrogen reacting with OH radicals producing H atoms. And that inhibits reactivity at low temperatures. Why? Because it consumes OH radicals producing a H atom. And at low temperatures, H atom reacts with O2 to give HO2. It doesn't go to chain branching. Whereas here we see the reaction of the N-alkanes, propane, butane, or pentane with OH enhances reactivity. Why? Because we get the daughter radicals, then we get low temperature chain branching reactions, and we get higher reactivity at lower temperatures. And hence, adding hydrogen to alkanes at lower temperatures decreases reactivity. Okay, so we've also studied then the effect of hydrogen addition on a large alkane ignition and flame speed. And we actually took ignition delay time measurements for hydrogen n-decane in air at 30 bar and 5 zig to 1. And what we see here is that hydrogen is very slow to ignite, but if we add just 5% n-decane as a pilot fuel, we see that the reactivity is greatly enhanced. And then if we add more, 80% hydrogen and 20% n-decane, we see again that the reactivity is enhanced even further. These blue symbols are actually pure n-decane, and what we see is that it's similar to reactivity as adding 20% n-decane to hydrogen. So once we've added 20%, we've more or less seen the effect of n-decane ignition at lower temperatures. But again, what we're seeing is the higher hydrocarbon enhances the reactivity of hydrogen at lower temperatures. Okay, and is a good pilot fuel for hydrogen at lower temperatures. Okay, and this is a new Gong at the symposium in 2023 showed, this is just a computational study, and they show that n-decane is fastest to ignite at lower temperatures, whereas pure hydrogen is slowest to ignite. And then again, the turnover temperature here is about 1100 Kelvin, 1150 Kelvin at 30 atmospheres, and then at temperatures above that, pure hydrogen is faster to ignite, with the n-decane being slower. And that's what we've seen for the natural gas mixtures and also here for n-decane in our study here. Okay, so we also looked at n-decane then at 5.5, 1, and 2, and at all conditions, we're seeing that the reactivity of hydrogen is enhanced by the addition of n-decane at lower temperatures. And here again, lines are model predictions, the points are experimental results, and you can see that certainly at stoichiometric and rich conditions, we're capturing the data very well. At the lean condition, we're slightly over predicting the reactivity of the mixture. Okay, and then again, if I go back to the study of Gong et al. And the effect of n-decane addition to hydrogen in terms of flame speed, if we just add 10% n-decane to hydrogen, the flame speed decreases from about 1200 or 1100 centimeters per second here at the peak all the way down to 850 centimeters by just adding 10% n-decane to it. These are just, again, model predictions, but I would be confident that these are probably quite accurate. Okay, so we've also in version 4.0 added ammonia chemistry. So we've looked at a lot of ammonia hydrogen mixtures. I'm going to go quickly through these. These are ignition delay times for pure ammonia. Again, the points are experimental results, the lines are model predictions, and we're capturing very well the ignition delay times that are measured here. These are for pure ammonia. Then we have ammonia hydrogen mixtures, and again, the model is capturing the experimental measurements very well for different studies here. These are two different publications, one from 2021, the other from 2023. The model's capturing the data well. At lower temperatures for pure ammonia and higher pressures, the ignition delay times are well captured. And again, here for ammonia hydrogen mixtures where data is available, again, the model is capturing the data reasonably well. Certainly, we're getting the quantitative agreement, and so here we've pure ammonia, and then the more hydrogen we add, the faster the reactivity of the mixture, and that is being captured well by the model. And you can see it here also. Okay, then also for pure ammonia flame speed, again, the points are experimental measurements, the lines are the model predictions. You could say here at higher temperature, we're over predicting the flame speed slightly, but particularly for ammonia hydrogen mixtures, we're capturing the measured flame speeds very well. Okay, and it's unlikely that ammonia would be used on its own. We've also looked at speciation data. There's very limited speciation data in the literature, but where data is available, we have very good predictions of it by our model. Here's our pyrolysis ammonia mole fractions versus time, and here are different mole fractions of different species versus time, and the model is capturing all of these quite well. Okay, we've also looked at ammonia methanol ignition delay time and flame speed. Again, we're adding the more methanol that we add to ammonia, the faster the reactivity, and that's been is predicted well by the model. Okay, so this is a 95-5 mixture, this is a 90-10, and this is an 80-20 ammonia methanol mixture. And again, the model is capturing that behavior very well. And here again, although in some cases we're not getting the quantitative measurements exactly right, we're certainly getting the qualitative differences in the reactivity well predicted by the model in all of these 6 different cases shown. We also then have ammonia methanol flame speed measurements. The solid line is our model predictions, C3 Mech version 4.0. The dashed line is the mechanism that was actually published in the study where they took the measurements. And in some cases, we're actually doing better than the model. In a lot of the cases we are, but in some cases we're not. Okay, but generally we are. And the model is capturing the differences for the different blends. Here's an 80-20 ammonia blend, a 60-40, a 60-40 methanol ammonia, and an 80-20 methanol ammonia blend. And again, the model is capturing that behavior very well. Okay, we've also looked at ammonia and heptane ignition, and here these points are for pure n-heptane, and then if we add 20% ammonia to the mixture, the reactivity decreases. If we add 40% ammonia, the reactivity decreases further. And we can see that the model is capturing the decrease in reactivity very well, and it's predicting that. Okay, and these are for a series of different conditions. This is at 10 bar, 15 bar. This is at a different condition of ammonia, 40% ammonia, and we're capturing that behavior well. For methanol and heptane blends, so if we want to look at, so this is n-heptane, we have pure methanol, and then we look at the antagonistic effect. So if we add 67% methanol or 50-50 blend or 25% methanol, you can see how the methanol inhibits the reactivity of n-heptane. Or if you want to look at it the other way, n-heptane promotes the reactivity of methanol. So but the idea here is that we're trying to explore the blending effects of these two and see, are we capturing accurately the blending effects if we have different compositions of these fuels in the mixtures? And for all of these different cases, 10 bar, 20 bar, 30 bar, for different mixtures, you can see that we are actually capturing very well the reactivity for all of these different blends. Okay, and also similarly for laminar burning velocity, on the left here we have flame speeds for pure N heptane. On the right we have flame speed for pure methanol, and here the points here are the flame speeds for different blends, and you can see at two different pressures, 1 and 2.5 bar, we're predicting the increase in flame speed by the addition of methanol. That's very well predicted. We also look then at the effect of NOx addition for EGR on different alkanes. So here we're looking at n-pentane and n-heptane. And what we see is that the reactivity is decreased at lower temperatures. So the red points here are where we have just pure n-heptane. And if we add NO to the mixture, we decrease reactivity at low temperature, and then we enhance it at higher temperature. The lines of the model prediction. So the decrease in reactivity is predicted well by the model at low temperature, and then the increase at higher temperature is also predicted well by the model. And here again, these are this is another set of data from the same study from Gladys Mardiak, published in 2006. Again, the decrease in reactivity is predicted at lower temperature, and the enhancement in reactivity is predicted at higher temperature. Okay, we have then ignition delay time validations for ethanol targets. These are all for pure ethanol. You can see again, for over a wide range of conditions, we're capturing the experimental measurements very well by the model. And also for jet stirred reactor speciation data and for flame speed measurements, we're also capturing the data quite well. And then if we look at methane dimethyl ether mixtures, again, dimethyl ether here is very reactive, methane is very unreactive. And then here we're looking at blends of the two in between, and you can see that the decrease in reactivity when we add methane to DME is well predicted by the model. Okay, we also looked at ethanol DME blends, and again, ethanol is very slow, DME is very fast, and in all cases, then if we look at a 70% ethanol, 30% DME, or a 50-50 mixture, they have intermediate reactivity, and that's well predicted by the model. So if we want to look at blends of ethanol DME or DME blending with other components in the mixture or in the mechanism, we would be pretty confident that the mechanism is performing quite well. We also looked at cyclopentane DME mixtures. Again, the points are experimental results, the lines are model predictions, and you can see for all of these different cases, we have good agreement. So here's a 70% cyclopentane, 30% DME. Here we have 30% cyclopentane, 70% DME, and we're capturing the behavior of these mixtures very well by the model. Okay, we've also looked at toluene DME. Again, DME is very reactive. Toluene is quite unreactive, lower temperatures, and the antagonistic effect of toluene on DME is well predicted by the model in all these cases, phi is equal to 0.5, phi 1, phi 2, all at 20 atmospheres. And the model's predicting that quite well. We've looked at primary reference fuel mixtures. Here we have n-heptane, isooctane, and then mixtures of the two, and they're well predicted by the model. And then toluene primary reference fuel mixtures, where we add toluene to the n-heptane and isooctane, and again, they're well predicted. The model is predicting data very well. We've also looked then through Polimi and Aachen, we've looked at a series of polyaromatic hydrocarbon and soot formation for a series of different reactors over a range of pressure, temperature, and equivalence ratios for lots of different fuels tested over a wide range of temperature, pressure, and equivalence ratio. And what we see here again, we've improved the predictions of the toluene oxidation mechanism. We've just for pure toluene, and also, as I've just shown you, for the TPRF mixtures. Initially, actually, the version 4 model performance was slightly faster for cyclopentadiene and actually too fast for benzene. So when we developed it initially, the model wasn't performing well. But by looking again, we were able to recover the C3 MEC version 3.3 predictions, and now our model is actually in better agreement with these data for benzene ignition delay times. for benzene oxidation and jet stirred reactors. Now the symbols are changed, they're reversed. Apologies for this. The dashed lines are the current model predictions and the solid lines are previous model predictions. But you can see actually in many cases, the dashed line predictions are better than the previous model predictions for many of these cases. Because again, we're looking at speciation data here in benzene oxidation jet stirred reactors. We've also looked at PAH predictions. And again, here, for instance, the C4H2 predictions are much better than they were previously with the current model. It's not true for all cases. In some cases, we're now over predicting here this C2H3CHO, the vinyl acetylene, is not well predicted by the model. It's over predicted. Okay. But in general, the model is actually, we've either retained the good agreement or we've improved a lot of the species here. Here again, there's some improvement in these species C4H2, C4H4, that they're better predicted by the model. In other cases, then we're still over predicting butadiene, but anyway, in general, we're retaining the good agreement or we're improving things slightly. And then this is just one final slide from Heinz Pitch's group where we look at parity plots. So what they do is here they plot the simulated concentration of a species on the y-axis versus the measured concentration on the x-axis. And if there's perfect agreement, we would have this solid black line. And then these dashed line are our predictions within a factor of 2, and this outer dotted line is our predictions within a factor of 5. And you can see in most of these 1, 2, and 3 ring species, we're within a factor of 2 mostly for most of these species. Sometimes they fall within the factor of 5, but in general, we're within a factor of 2 for a lot of different flames like butadiene, acetylene, aniline and propyne, butene with acetylene, butene with methane, butene with propene, ethylene, toluene doped ethylene and cyclopentene, and n-heptane species. Okay, so these are all premixed flames and over a wide range of pressures and temperatures typically. Okay, so at that I'll finish and thank you for your attention.
Thank you, Henry. In this session, we'll look into CONVERGE Studio and look to extract some of these mechanisms in the presentation. So the first thing that we do is open CONVERGE Studio. You can go into chemistry menu of CONVERGE Studio by clicking on this button. It's going to take you to the chemistry menu of CONVERGE Studio. Click on the new case. Now you can click on the C3 mechanism. Here, CONVERGE gives you the option to extract these individual mechanisms. For example, if you want to extract the hydrogen mechanism, you can simply click on the hydrogen. And now it's going to tell you how many species are there. We can select different versions of C3. Now you can extract the mechanism file, that is your mech.dat, which contains all the species and the reactions. Therm.dat file, which contains the gas phase species properties, and the transport.dat file. Now, the next thing that you need to do is define an output directory. Once you define an output directory, it's going to, and you can click on extract. Now, if you click on extract, it's going to extract the mech.dat, the therm.dat, and the transport.dat file for you. We can also extract other mechanisms like methanol. So if you click on methanol, it's going to give you 40 species. Similarly, if you want to extract n-heptane, like we saw in the presentation, this gives you the option to do that. Now, if we are doing a dual fuel simulation of n-heptane and methanol, you can click on both of these species, and you can basically define an output directory and then extract the mech.dat, therm.dat, and the transport.dat file. Now here, if we want to do a dual fuel simulation, we can see that with n-heptane and methanol, the starting number of species is 1949. So the next thing that we need to do is reduce our mechanism so that we can do CFD simulations. So CONVERGE Studio offers you the mechanism reduction tool that you can use to reduce your detailed mechanism. So the way we do that is click on the mechanism reduction tool, activate mechanism reduction, and then you can either choose the gas.dat or the transport.dat for your species diffusion model. We click on OK. The first thing that we need to do is we need to import all the term.dat, transport.dat, and mech.dat file that we just extracted from the C3 tool. So I click on this button here, and then I go into my directory. This is where I saved my files. So I'm just going to extract, import those files here. And the reaction mechanism file. So now you need to set your mechanism reduction inputs. So the way we do that is click on mechanism reduction. So these are like different mechanism reduction algorithms, DRGAP, sensitivity analysis. So we just enable those. The first thing that we need to do is we need to define the target species that we want to keep in the reduced mechanism. So they would be your fuel and oxidizers. So here we're doing dual fuel simulation of methanol and n-heptane. So we would need methanol and n-heptane. The next thing that we would need to define are the oxidizer species, which is going to be air in this case. So nitrogen and oxygen. In addition to that, you can keep other additional species, so carbon zero atoms, and you can define a weight for them. So if you click on this, so it's gonna populate your target species section with all these C0 species, and you can always like manually select to delete some of these species and just keep some of these species that you need. And you can also like alter the weight of these. So you can put a lower weight to some of these species, but for your fuel species and oxidizer species, you need to keep a weight of 1. And now the next thing that we do is go into this cases tab. So the mechanism reduction is based on either ignition delay or laminar flame speed. We have other options as well, but we're going to be focusing on ignition delay and laminar flame speed in this session. So the way we do this setup is we click on add and we select type. So the first type we're going to select is ignition delay, constant volume. So when you select ignition delay, it's gonna on this right window on the right hand side, you need to define the DRGAP error. So it's basically the error tolerance between your detailed mechanism, that is the mechanism that you're starting with, and the mechanism that you will be reducing. So let's define an error of 15% for the ignition delay. And now we need to do a 0D case setup. So these are like ignition delay cases. You can easily do that by clicking on generate case tool. We can define a certain temperature range, a pressure range. In this case, I'm going to define 40 bar to 160 bar with a range of 20 bar. Valence ratio, I'm just going to keep this value. Now the fuel species, I'm doing a dual fuel simulation here, so I need to define my two fuels. It's going to be methanol and heptane. So I can define like a different ratios. So this is where the what the user wants. So if you want like 30% methanol and 70% diesel, or if you want 20% methanol, 70%, 80% diesel, you can do that by changing the amount of mole fractions. Oxidizer species, you can directly add air here. And the next thing that I do is just generate cases. So it's going to come up with a number of different 0D ignition delay cases. So if we are interested in any different ratio of the fuel, then we can change that here. So I can change that to 0.2 and 1 and click on normalize. Now, if I want these cases to be added in my 0D setup here, So I can click on 0D generate cases, and if you click on no, it's going to add to your existing cases. So it's going to create like more cases here with like a different ratio of your methanol to n-heptane ratio. The next thing that we need to do is the 0D solver setup. So since we have species number is greater than 100, so we're going to be using the iterative converge solver. That should be okay. So this is ignition delay type. The next type we'll add is the laminar flame speed type. So again, we need to define ADR-GEP error, which is going to be 15% in this case, and a sensitivity error. We also need to define the when you set up this 1D case setup menu. So we again go to the generated case tool. Start with 40 bar to 160 bar with a range of 30 bar. Equivalence ratio is going to be 0.5 through 2, the range of 0.2. Fuel, we're going to use methanol and heptane. And we're going to use oxidizers, and then we're just simply going to click generate case tool. So this is going to populate with several laminar flame speed cases. We click on OK. We can look into the solver setup, and these are like some of the settings that we need to be using in this. We will be using during this mechanism reduction work. So after this, you can simply click on the click OK, and this is set up. So now you can export your project files to a directory, and then you can run the mechanism reduction utility and get your reduced mechanism. So here we did this mechanism reduction process for 6 different times, and the number we reduced to was 103 species. We did not tune the ignition delay and laminar flame speed to match with the parent mechanism. Parent meaning the mechanism that we extracted initially. So we Converge also offers you the option of doing mechanism tuning. Thank you for your attention.